In this video, I want to present the physics behind the Bear Grylls trick to find north using the sun. So the trick goes as follows. You're lost in the middle of the woods and you want to know, maybe not in the middle of the woods because that won't work very well, but in the middle, you're lost somewhere in nature and you want to know where the north is. And you're in the middle of the day, so you have no idea where the stars are. You cannot use the North Star. So the trick goes like this. You stick a stick into the ground and you look at the position of the shadow of the tip here at a certain time. You wait a little and the sun will have moved and now your shadow will be somewhere here. You trace a straight line in between these 2 points, and this straight line is said to point east-west. So perpendicular to this, you can find the north. So the first thing, when you see tricks like this, you have to try to make sense of it. Does it make any sense? Is it possible that it's true? Well, there are places on Earth at certain time of the year where the sun will just go from east to west in a circle that passes directly overhead. So if you're soft enough and you're at the right time, the sun will have this trajectory. It will start to the east, go up just over your head and then come back. And of course, in these situations, the shadow at one time will be there and a bit later it will be there, and there will be a straight line that's directly oriented east-west. So that makes sense. In some situation that will work. We can see that there are other situations where that will work anywhere on Earth, is when you're close to noon. When you're close to noon, with this again, east, west. If you're close to noon, the sun will go here, and there will be, at noon, there will be a shadow that will go to here, and a bit before noon it will be here, and a bit after noon it will be here. So this too would work. If you're just right before noon and right after noon and you trace a straight line, it would be oriented east-west. The sun doesn't even have to rise to the east and set to the west. It can be a bit this way, a bit this way, but it's symmetrical. So the symmetry of the trajectory of the sun makes it this trick works exactly. But now, are there places on Earth where that will not work? Well, that will not work if you're lost in the middle of the tundra, way up north, in the summer when the sun doesn't set. Because if the sun doesn't set, there will be some points in which the sun is directly to the north, for example, or directly to the east, and it's still up. Like the sun will, if you, again, we do our representation of the Earth, the sun never sets. It goes around like this. So if the sun is around here at the east, well, their shadow will be here and here, and if you do a straight line in between, well, you're not going into the right direction. The line points north-south instead of east-west. So this trick will not work all the time. So how can we know how precise the trick is, and why does it work? So that's what we'll see on the next board. Okay, so basically what we need to know is the shape that the tip of the shadow makes on the ground. Because if this shape is, for example, a straight line that goes east-west, the trick will work all the time. If the shape is different, then there will be times at which it won't work and times at which it will work. And if we know what the shape of the curve is, then we can know what our error is and make corrections if we want to, and see if we should rely on the trick at all or not. So that's a bit tricky, but the way to see it is that, let's suppose you have the Earth here and you have the sun. Of course, the sun is very far. I cannot trace something very far. It's not to scale, but it's very, very far from us. So what is the trajectory of the sun given by the Earth's rotation? Well, if you are on the Earth, as the ancient people believed, it looks like the sun is going around you. So what will be the trajectory of the sun? It will be a circle centered on a point that's along the axis of the Earth. That's what happens. If you rotated the whole universe around the Earth, well, the axis of rotation is the Earth's rotation axis, and everything seems to go around a circle centered on this axis. That's why you see the numerous astronomical photograph, long time exposure, you see the trace of the star that seems to rotate around the North Pole. Well, the sun will do the same. It seems to rotate around the North Pole or the South Pole, depending on where the sun is. Now, this is a circle, and it rotates around that axis. So if you take the center of the Earth, every point here, 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 if you look at these points, they will form a cone. What is a cone? That's what happens when you take a circle and you join every point on the circle with the apex of the cone. So this thing here will form a cone. How is that useful? It's because we want to know what is the trajectory of the sun with respect to the point of our stick that we had before, and then we can see what the shape of the shadow is. So if this is a cone centered at the center of the Earth, we can say that this will be the same shape centered on our stick. So why is it? It's because the sun is very, 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 very far away from the Earth. The distance between the Earth centers and the sun is much larger than the radius of the Earth. So basically, if the sun is making a cone with the center of the Earth due to the Earth's rotation, this will be the exact same shape with a small, very small difference for any point on Earth. Here, here, here. Since if we draw this to scale, it's like the Earth will be that, not even to scale, but to a better scale. That's the Earth, and the sun is here, and it rotates this way. So the cone with the center of the Earth, or the cone with the point at the surface of the Earth, will be almost the same. It's indistinguishable. So the sun will define a cone in which the base is in the plane in which the sun rotates, relative to the Earth, and the apex will be here at the tip of our stick. So how is that important? It's because we want to know what the shadow is. So I will just erase this and we'll get to the next board. So on the previous board, we convinced ourselves that the sun would draw a cone with respect to the tip of our stick that we stuck into the ground. So we have a stick here, it's got a tip, and the sun defines a cone. So why is it important? It's because a point linking the sun and the tip will allow us to determine where the shadow is, because what the end of the tip of the shadow is basically where is the position of the last ray, because the rays that go here, well, will be blocked, they will create a shadow. The rays that go this way, they will be blocked, they will part of the shadow, but the rays that go this way, the way that just grazes the tip here, will be at the end of the shadow. So that's the shadow. And here, the tip will just, and here, so the ray that just grazes the tip of the stick will hit the ground at some point. So what are these rays? What shape do they form? Well, we have a cone, so we have the tip of our stick here, and we have the sun defines a cone, because when the sun is at this time of the day, the ray will be this way. When the sun is at this time of the ray will be this way, and when the sun is here, for example, the ray will be this way. So basically, what happens is that you define another cone. So if there were no Earth, there was no ground here, these rays will span a cone in space. Basically, if you have the Earth and you have the sun here, there will be a ray that will go this way, there will be a ray that will go this way, and so on, and we get another cone. So where does that get us? It gets us to the fact that here, what we want to know is what is the intersection with the Earth. And we say that's a very complex problem, but when you're lost in nature, the Earth appears to be completely flat. The curvature of the Earth is not important. So your shadow will be at the intersection of a cone given by the sun. So the trace of the tip of the shadow on the ground will be at the intersection of the cone that's formed by the sun and the ground, which we can approximate as a plane. And what is the intersection of a cone with the plane? It's what we call the conics. It's either an ellipse, a circle, or an hyperbola. So if you remember when if we had a cone and we have a plane that intersects the cone, if the plane intersects the cone here, the shape of the intersection is an ellipse. If the plane intersects this way, then it's a circle if it's perpendicular to the axis of the cone. And if the plane intersects in a way that doesn't cross both sides of the cone this way, the shape is an hyperbola. So that's basically the definition of what an hyperbola is. The circle and the ellipse will correspond to the cases in which the sun doesn't set. So the tip of the shadow will form a closed curve, which will be either a circle or an ellipse, depending on where the sun is. And if the sun sets, so which is in most latitudes in which you would want to use that, the shape will be an hyperbola. So this just took a quick look at what these will look like, and then I have an exact example to present at the end of the video. So this is the shape of the tip of the shadow that's given by this stick at different times as the sun will go from east, or from the sunrise point to the sunset point here. And here is the south is midday, it's what happens around noon. So we see that if we're around noon, as we discussed earlier, here the curve is almost east-west. And basically what you do when you take the position of the shadow at two different very close moments, what you do is you basically take the tangent to this curve, and here this curve will be east-west. Now, as you get closer to sunrise or sunset, you will deviate from this. You see that if you're very close to sunset, basically you're to sunrise, you're pointing towards the sunrise. And if you're very close to sunset, you will be pointing towards the sunset. These are given by the asymptotes of the hyperbola for people who know about these concepts. So the closer you are to a sunrise or sunset, and the further away the sun is from rising and setting directly east or west, the worse your approximation will be. So if you're at the equinox, where the sun rises to the east and sets to the west, we're talking about the northern hemisphere here, then your curve will be a straight line here, oriented east-west. It will be exactly like this. And you will have an exact method of finding where the north is. If you get close to the solstice, where you will deviate the most from this ideal pure east-west curve, then your approximation gets worse. And on the next board, I would show an exact curve of what this looks like and what the value is. So here we have the exact curve, exact shape of the shadow of a stick planted vertically at a location that's about 37.5 degrees of latitude at different moments: winter solstice, equinox, and summer solstice. And you see that the deviation can be relatively large. I calculated that if you are at about 45 degrees latitude, the deviation can be about 25 degrees. But you can say that, well, first, this is a worst case scenario. The closer to get to the equinox, the better it will be. And if you know that this is the case, you can see that the curves kind of shift away from pure east-west pretty rapidly. So you know that if you're close to noon, you're pretty good to east-west. And if you are late in the afternoon or early in the morning, you will be directly or almost directly oriented towards where the sun sets or rises. And if you know the time of year and your latitude, you can prepare in advance, and you can see that this will be about 20 or 15 degrees or something like that. And I think that trick works. You have to correct a bit if you are close to the solstice, but you can approximate it, for example, by remembering that at 45 degrees latitude, you are off by about 25 degrees at the solstice. So if you know the date, you can get a kind of an approximation. It won't be exact, but this method is by no means meant to be exact. It's just to have a good idea of where north is, and also to be consistent, probably, so that you don't walk in circle in nature. That's a tendency that people have. When they get lost, they start walking in circle. So you can either correct or just use it and say, I know I'm wrong, but if I keep the north always at the same location, I know I'm probably off by a few degrees, maybe 10 degrees, 20 degrees, but if I keep the north always the same place, I will not walk in circle, and in ways you're lost. So having an exact orientation is probably not something that's required. And that's it for today.